Okay, well, welcome. So one thing Jason didn't mention is that EMU Technologies is also working on a port of GraphBLAS. And what is GraphBLAS? Well, GraphBLAS sort of turns everything on its head. You know, I'm used to solving AX equals B. On the outside, it's matrices. On the inside, we know it's all cliques and trees and graph algorithms. Well, this just reverses that altogether. And so GraphBLAS, what it does is it provides a powerful and expressive framework. Think of MATLAB for graphs, for creating graph algorithms using the mathematics of linear algebra over summerings. And then when applied to sparse adjacency matrices, these algebraic operations are the same as computations on graphs. So consider a breadth-first search, starting here at node 4, with the frontiers of nodes 1 and 3. So the next frontier is nodes 2 and 6. Now, this traditional algorithm here on the left is easy to state and write, but as graph algorithms get more complex, this node and edge-centric model gets harder and harder to write, particularly in parallel. So the key observation is this BFS has the same workflow as a matrix vector multiply. So take the vector Q in green with entries 1 and 3 present and multiply it by A transpose. Now this gives the set union of outgoing edges from the frontier in green with entries 2, 4, and 6 in red. Now node 4 needs to be excluded, and it's excluded in the if test in the traditional BFS. This translates into a matrix mask where only entries without a parent are allowed into the final result. Now, you would think that I could do matrix vector multiply, right? Multiply A transpose times X and I get a 3. What is going on here? Well, this is a different semi-ring. I'm using here the any second I semi-ring. So the multiplicative operator, we rip it out, and instead of times, we put in the second I operation, which returns the row index of the second input of A times B. So it's the value K. It's the index K from the multiplication. And in the BFS tree, the BFS says, well, any parent will do. Now, node 2 has the parent of 1, node 6 has a parent of 3, so this will just give us a result 1 and 3. But if we had multiple parents, then just pick any one. And this allows for a benign race condition internally, so it allows for better performance. Any parent will do. And that's the reduction. Instead of summing up the results, you just pick any one. Now, the primary GraphBLAS operations include what you might find in MATLAB. Just throw away the summaring and put in something else and then use a mask. These primary operations includes matrix multiply, element-wise operation, extract, assign, and so on. They can all be used with a mask, many different data types, integers, floats, user-defined operators, user-defined summarings, user-defined types. Different summarings appear in different graph algorithms. The BFS, as I showed you, uses the any second I summaring. A shortest path problem uses min plus, and many more. Graph algorithms are they're mostly simple to write in GraphBLAS via its C, MATLAB, or Python interfaces, and I'll give you examples of those. And yet it has performance that rivals specialized, highly tuned parallel kernels, which only a handful of experts, and I'm speaking to a lot of them, can write. This already appears in commercial products. It has a large and growing community behind it. NVIDIA, Intel, Redis Labs, IBM, MIT Lincoln Lab, many others. I mentioned EMU Technologies is working on theirs as well. So high-level languages like MATLAB and the BLAS have transformed high-performance computing, and the GraphBLAS vision is to create a groundbreaking transformative shift in how graph algorithms are expressed as linear algebraic operations over summarings applied to sparse adjacency matrices, giving us a powerful high-level abstraction in which we can easily write complicated graph algorithms while at the same time achieving a high level of performance. So how do we do this? Well, here's a slide from a talk I gave a while back, not long ago, work with Tim Matson at Intel and Michael Pelletier on a Python and MATLAB interface to GraphBLAS. And so imagine you just want to do A times B with the min plus summaring and with a mask. Well, the C API looks like this line here. The Python and MATLAB are here. Now in MATLAB in particular, if you use the default conventional summaring, just use star. If you don't have a mask, just there it is. It's just a single overloaded operator. And in MATLAB and Python as well, if these are operations or the inputs are defaults, you can leave them out. So it's simpler. And here's an example of PageRank. Here's PageRank in Python on the left, MATLAB on the right. And here I'm using the plus second summaring in both cases. So the plus is the conventional linear algebra, but second. Why? Because A times X, I just want to grab the value of X. It's like 1 times X if it's in the matrix A. So treat the matrix A as binary is what that operator is saying, and that saves me a memory load. I don't have to read the value of the matrix A. I can consider just its structure.
Can you
And
hear my timer?
yes. So the what kind of performance we get in MATLAB? We can get A times B, 30 times faster. Competing with myself, I wrote both of them. Matrix indexing is about can be 1,000 times faster than MATLAB. The masking operation is maybe about 100,000 times faster. This can take 7 seconds in the matrix with 100 million non-zeros, and it took a week in MATLAB, and it never finished. So, which we can fix that because we can fix this too, I hope. So anyway, very exciting performance and exciting formulation. Thank you very much.